out of Chapter 9 was this mole-mole relationship. Okay? That is what Chapter 9 was really all about. Okay? It gives you one conversion factor, or one relationship. That relationship changes depending on what you're looking at and what you're looking for. So all the chemical reactions that we work with, okay, all of them generate new conversion factors. We have a relatively short equation here. Okay? Just nitrogen plus oxygen goes to 2NO, or nitrogen monoxide. Okay? Within that simple equation, we have 6 conversion factors. Textbook actually put these together wrong. This is a 2. Those 6 conversion factors allow us to now convert a whole lot of different things, different directions. Which one of those should we use? Okay, well, to decide that, it depends what we're trying to get. Okay? It also is going to depend on what we're starting with. So you have to realize that balanced equation sets you up with those individual conversion factors. You then get to manipulate and decide which one of those to use in the case that you're looking at. Okay? The big thing behind your your balanced equations, it is the only conversion factor that allows you to convert between one substance, substance A, and substance B. The only one. You must go through a balanced equation. Every other conversion allows you to change, say, grams to moles or to atoms, okay, or milligrams, nanograms, okay, kilograms. You can do all of those conversions without needing a balanced equation. As soon as we change the substance, you must specify through a balanced equation that conversion. Okay? So let's take a look at a couple examples, or maybe just one. Okay, so if this was our question, how many moles of oxygen react with 2.25 moles of nitrogen? Okay, so the first thing that we'd want to do is identify what stuff we've got going on in here. We're looking at moles of oxygen, and we're looking at moles of nitrogen. Do we have a problem with that right away? How do I convert between the moles of oxygen and the moles of another species? How do you convert between 2 different species? What's that? The only way that we can convert between 2 different molecules is with a balanced equation. Can we solve this problem right now? No. We need the balanced equation. Without the balanced equation, this problem is impossible. You cannot possibly solve this. Okay? So thankfully, next tab, we've got a balanced equation. Okay? Or we've got an equation. First thing that you should check, is it balanced? Yes. Okay? That whole balancing chapter, chapter 7, you had lots and lots of practice with balancing. Why? Because to do anything in chapter 9, you have to have a balanced equation. So if it takes you half an hour to balance the equation, you've now just wasted half of your exam time to not even get to the question. Okay? You have to be able to balance and verify that something is balanced extremely quickly. And that requires practice. Okay? So now what we can do is start to piece the problem together. Where do we start all of our problems? With our answer. What do we want as our answer? Moles of oxygen. What should I be writing? O2. If I was asking for just O, it would say moles of oxygen atoms. Okay? It has to specify that extra information. Okay? Oxygen is a diatomic molecule. If it's going to react, it's going to show up in its elemental state. Okay? So we're looking at moles of O2 being our answer. Where do we move to now? What we're starting with. Okay? And here's where I'm going to get kind of obnoxious with things. Okay? What do we start with? Okay? Everybody's going to give me that number right away. Please don't. The numbers are not important. Okay? What we're concerned about are the units. What are the units that we're starting with? and someone whispered it over there, kind of drowned out by everybody saying just moles. This is why writing the substance is important. If I just write moles, what's my answer unit? Moles. What's my starting unit right now? Moles. Hey, what's my answer? Oh, it's 2.25. Really? Okay, could be. Could have lucked your way into an answer, but is it really moles that we're starting with? It's moles of N2. Do your units match? No. Okay, you must specify that substance so that you know you have to do some extra calculations. Okay, that is it as far as our unit goes. So now we can volunteer the number and we can slide that in as our 2.25? 2.25. Okay. Do our, work with me, units match? Come on now, there it goes. Okay, our units do not match, which means we need to convert. Does moles of N2 show up in our answer? No, which means in our conversion factor, what has to happen? It must cancel. For it to cancel, I need moles of N2 on the bottom. You'll notice at no point have I asked anything about a number, just looking at the unit. What unit do I want as my answer? Okay. Always put your target up top. Okay. Now comes an important question, and this question doesn't always work. Is there a relationship between the moles of O2 and the moles of N2? Yeah. That relationship comes from the balanced equation. So yes, I do have a relationship. What if that answer was no, I don't have a relationship? Okay. At that point, that means we need multiple, or we need at least another conversion. It's going to require a little bit more work, and we'll look at that in a little bit when we need to get to that question. Okay? So now that we've got our unit set up appropriately for this conversion factor, let's make sure we put some numbers in here in the appropriate spot. What is that relationship between the moles of O2 and the moles of N2? How do you know it's 1 to 1? We go to the balanced equation and we look at the numbers in front of those two species. What are those numbers? Ones. So the number in front of N2 is? What number should show up in front of moles of N2? What number shows up in front of O2? What number should show up in front of moles of O2? 1. Okay? You'll notice if we go back to the equation, or the question, it says moles of nitrogen, and it says the number is 2.25. Why did I not write 2.25 down in that denominator? It's a trickier question. We're focused on the conversion factor and the conversion factor alone. What is the relationship between those? Where is that relationship found? In the balanced equation. Where is that 2.25 found? In the question. Okay? That is irrelevant to what we are trying to solve. We are trying to figure out the numbers for our conversion factor. Those numbers come only from the balanced equation. Nothing else in the world is important. The only thing we can look at is the balanced equation. Do not start bringing in those other numbers. Okay? What happens with our units? Our moles of N2 cancel. And if we look at our units, what would our units be? Moles of O2. What was the answer that we wanted? Moles of O2. Do we have the correct units? What can we do now? Use your calculator, do all the mathematics that you need to do. Multiply everything in the denominator or the numerator by itself or by each other. Multiply everything in the denominator so you end up with two numbers. You can then divide those two numbers. All right? And the answer we would get, 2.25 moles of O2. Okay? That was a bit silly. That was a 1-to-1 ratio. That was kind of boring. So let's switch it up. Let's make it a little bit more difficult. I don't want the moles of O2. I want the moles of NO. Okay? Zach's exact same format. Thankfully there's no Zach's in here. Do my units match? No. So what do I have to do? Need to set up my conversion factor. What unit shows up in the denominator? Why moles of N2? We need it to cancel with the earlier one. What is the target unit that I want? Careful. I want the moles of NO. Is there a relationship between the moles of NO and the moles of N2? I don't even want to hear that quite yet, but you're right. There is a relationship. Where is that relationship found? In the balanced equation. Now we get tunnel vision. The only thing we can look at is the balanced equation and that conversion factor. What number shows up in front of our NO in our equation? What number needs to show up in front of the moles of NO in our conversion factor? 2. It is a direct relationship. What happens with our moles of N2? What number showed up in front of that? 1. What number shows up in our equation? 1. Now what do? Check our units. Moles of N2 cancel. What units do we have? Moles of NO. What was our answer? Moles of NO. Do we have our correct units? Yes. What can we do? Now we can go through and deal with our calculator, do all the multiplication and division that we have to. Okay? Take advantage of that balanced equation to convert between substances. If you don't have to convert between substances, do we need a balanced equation? No. The only time you need the balanced equation is when you're converting between those different species. Okay? So we can make this a little bit more difficult, which is what was on exam question F, I think. Okay? Looking at now a mass issue. If we attempt to look at this problem, we've got some interesting dynamics between this. We're trying to convert between the mass of mercury sulfide, species 1, and the mass of mercury thiocyanate, species 2. How do we convert substances? Through a balanced equation. You must go to that balanced equation to do that. What units does our balanced equation give us? Molecules, atoms, moles. It says nothing about mass. We have to convert our mass units into moles. Once we're in the moles, we can now convert substances, and we can generate the moles of our other substance and then convert it back into mass. Okay? It involves now a string of calculations. Okay? So, because it's kind of interesting, what we're going to do first, let's take a look at this. Anybody heard of this reaction before?
TNT.
No, TNT is trinitrotoluene. Okay. It's known as Pharaoh's snake. Should have rewinded the video back. Come on, YouTube. So what they've got here is inside a closed container. That's why they got the little terrarium there. Probably added all the cacti, kill the cacti. And they're putting down that mercury thiocyanate. And then what they're going to do is they're going to start it decomposing. How do we get things decomposing easily? Heat. So they bring in a torch and they start the reaction. Now what ends up happening? Okay, you get this kind of odd, bizarre, shape-shifting kind of process. Some of these videos are more interesting than others. It also looks kind of disgusting, which I think somebody said. Okay? depending on how the reaction actually works, you might see these nice long coils come off of it. It's kind of neat. What's happening in this process?
It's reacting with oxygen.
It's actually not reacting with oxygen. It's just the mercury thiocyanate decomposing. We've added enough heat that one of the species within that compound turns into a gas. Okay? The issue is then that gas wants to escape, but it has to escape through the other solids. So what happens? It starts to inflate the other solids as the gas tries to escape, and you see this weird snaking, growing kind of thing. Okay? So kind of an odd process, kind of neat. I have heard allegedly that you can find this Hogwarts? Probably not. But it is, what's that?
Was that sped up or was that how fast it actually?
That was actual speed, I believe. Yeah. It's known for typically for fireworks, so they used to sell it as a firework. You'd light it off and then watch this thing move around on the ride on the ground. Any ideas why they stopped doing that? Mercury is pretty toxic. So they stopped exposing people to mercury unnecessarily. You can find other versions of it. I think there's a carbon snake that does something similar. I think baking soda and sugar. It's nowhere near as exciting, just in case you were interested in trying that. So in the process of doing this, we generate off some of these compounds. I believe it's the carbon disulfide compound that's a gas, which is also a secondary reason why this reaction is not done very often. Anybody know what carbon disulfide smells like? It's rotten eggs, a really, really bad rotten egg smell. Okay, so it's another reason why we don't do it anymore. Okay? So what we are going to try and do is do this conversion now. So let's take a stab at it. Where do we start all of our problems? At the end. Okay? What do we want? We want the grams of our mercury sulfide. Here's where I would take one first big giant leap for simplification. Okay? Any ideas what that leap is going to be? HGS is an awful lot of letters for me to write. I'm going to write it as MS for mercury sulfide. Okay, not as big a deal for the mercury sulfide, a lot bigger deal for the next one. Where do we start? Grams of our mercury thiocyanate, which I can't even say right. Also way too many letters. I'll go with MT for mercury thiocyanate. Do my units match? No, so I can bring in my numbers. What number do I have in front of the grams of mercury thiocyanate? 1.25. Okay. My units don't match, so I need to do a conversion. Okay. Do my grams of MT show up in the product? No. What does that mean? Needs to cancel out, got to put it in the denominator. Okay. What do I want as my final answer? Grams of MS. Okay. For those of you frantically writing this is one of the things that's nice about digital stuff. I can erase it really fast. Do we have a conversion factor between the grams of a species and the grams of another species? No. The only way we can relate two different species is through moles, through our balanced reaction. We are not in a mole unit, okay? Which means we do not have that conversion factor, which means we can't convert to grams of MS, at least not right away. Okay, so this is where we run into that issue of no, we've got our wrong answer. Okay, so what do we decide to convert to? Okay, why do you want to convert to moles? Say that again. I actually think I liked what you were saying. Okay. Ultimately, what I would argue is we're going to shotgun this. Okay, I have no clue what that conversion factor is, but I know I have a conversion between grams and moles. Where do I know that conversion from? The periodic table. Okay? There are only one or two different conversions that we can go through with grams. Okay? So worst case, we shotgun, try one, whoops, that didn't work. What do? Somewhere further down the calculation, you'll end up reversing that calculation. That's fine. Okay? That means you have to do a whole lot more work, but you're at least following the units appropriately. Okay? As far as why we should get to moles, okay, the other answer is that how do we convert between substances? We have to be in moles. So a good first step to do, get it into moles. Okay? So what is the relationship now between grams and moles? Where do we find that information? We'd have to go to our periodic table. To do that, what do we have to do? We will look up the molecular mass for every single atom that makes up the compound mercury thiocyanate. Mercury has a molecular weight of 200.59. What's the next atom? Nitrogen has a molecular weight of 14.01. What's the next atom? Try again. There's another atom of nitrogen. How do you know there's another atom of nitrogen? Remember what your subscripts mean. Okay, so to fix that, we can now multiply by 2. What's our next atom? Carbon. How many carbons are there? 2, so we have to multiply that by 2. Next atom? Our sulfur, 32.07. And again, times 2. We add that all up. That number gets us 16.7. What are the units? Grams, ooh, good with that, of MT per 1 mole of MT. How do we use this conversion factor? What number in our conversion factors, or go back to our equation, we've got moles of MT on top. What number should show up in front of that? Why the 1, not the 316? Because the 316, if you look at that number, is on top, right? Why is it not on top in our conversion? Follow the units. The place will change. Where does the 316 show up in front of? Grams. Which means when we put that into our conversion, it must show up in front of our grams. What unit do we have now? No numbers. We have moles of MT. Is that our answer? What does that mean? We need another conversion factor. Do we want moles of MT in our answer? No, which means? Need to put it in the bottom. What do I want for my answer? Grams of MS. Can I relate the grams of a species to the moles of a different species? No. I can relate grams and moles of the same species, not for different ones. So again, bust out the eraser and we have to erase. What can I relate the moles of MT to? I can relate it to the moles of MS. Where does that relationship come from? From our balanced equation. What numbers do I need to put in there? The number that shows up in front of MS was 2. The number that shows up in front of MT, 2. Okay. What units do we have now? Moles of MS. Is that our answer? No. So yet again, another conversion factor. What do I want moles of MS in my answer? No. What do I have to do? It needs to be in the bottom. What do I want on top? Grams of MS. Can I finally do that conversion? Yes. How do we get that conversion? We need to add them up. Gut response almost always for a lot of people is to put in that 316. What's wrong with that? The 316 is a gram per mole value, but that is the gram per mole for MT. What do we want? MS. So we would have to go through and total up yet another situation. Take our mercury at 200.59, our sulfur at our 207, get our new molecular weight, 232.68, close enough, which isn't showing up. That's nice. Come on, I know you can do it. Grams, come on, per mole, there it goes, MS. MS. What number shows up in front of our grams in our conversion factor? The 232. Why? Because that's the number that shows up in front of our grams in our molar mass. What number shows up in front of moles? 1. Okay. Yes, that is there. There it goes. Okay. So you have to be able to propagate through all of these calculations. You'll notice that if we're going to try and convert pretty much with a balanced equation, which is pretty much everything that you're going to do within Chapter 9, and nearly everything that you would do in 151, involves converting substances. To convert substances, what unit do we need? Moles. So your first step for every problem, get it into moles. Okay? Once you're in that mole unit, you can now kind of propagate through. Doesn't always work, but that works as a pretty good first step. Okay? Questions about that? Okay, you guys seem awfully excited about that. Okay, so we got our limiting reactant concept. We've gone over the cheese and bread example enough, so let's actually make it chemical. Let's take a look at this reaction. Okay? We're going to put in some amounts as far as moles. I'm going to give you 1 mole of sodium carbonate, 1 mole of water, 1 mole of CO2. How many moles of sodium hydrogen carbonate can you make?
2.
Okay. Guess what kind of problem this is? Dimensional analysis, just like every other problem. So, what do we start with? 1 mole of sodium carbonate. What do we want to get to? Moles of sodium hydrogen carbonate. Do our units match? Nope. What do we have to do? Need a conversion factor. We need to get rid of moles of sodium carbonate, and we need moles of sodium hydrogen carbonate. What number shows up in front of the sodium hydrogen hydrogen carbonate? Oh my gosh. We go back to the balanced equation. What number shows up in front of our moles of sodium hydrogen carbonate? 2. So the number that we would need to put in there? 2. What number do we put in front of our moles of sodium carbonate? 1. How many moles of sodium hydrogen carbonate can we make? 2. Run the math. Okay? This is why we use dimensional analysis. A very common answer that a lot of people give out would be 3. Where do you get 3 from? Well, 1 plus 1 plus 1 is 3. Yeah, that math is absolutely valid. That does not match the chemical equation. Okay? Use the coefficients from the balanced equation to set this up. Okay? So now the next question. Let's make it a little bit trickier. Start with 2 moles of sodium hydrogen carbonate. How many moles of 2 moles of sodium carbonate. How many moles of sodium hydrogen carbonate can you make? So let's check our math. 2 moles of our sodium carbonate. We're trying to get 2 moles of our sodium hydrogen carbonate. Adjust our units. Sorry, I know it's getting crowded. What numbers do we need to put in there? 2 and 1, right, from our balanced equation. What answer do we get? 4. So that was a pretty good answer from most people. So the right answer? No. Let's see what happens when we look at our 1 mole of water. Same idea, we want to convert that now into, whoops, that was way too close to the edge, moles of our sodium hydrogen carbonate. Do our units match? No, so we got to do our conversion. Moles of H2O need to be on the bottom. Moles of our sodium hydrogen carbonate need to be on top. What number shows up in front of our moles of sodium hydrogen carbonate? What number shows up in front of our water? How do you know that? Use the coefficients from the balanced equation. We do that math, what do we get? 2. Interesting. What just happened here? How many moles of sodium hydrogen carbonate were actually made? Only 2. How come I couldn't make 4? When we looked at the sodium carbonate, I got 4. We didn't have enough of the other substances to actually propagate all the way through. So limiting reactant calculations calculations are a bit obnoxious because you have to go through and determine how much product can be made if we assume only one reactant, or that reactant is our limiting reagent, and we assume everything else is in vast excess. So when we looked at our sodium carbonate, we started with 2, we did our conversion, we got 4 moles of sodium hydrogen carbonate as a possibility. If we look at the water, we can only produce 2, which means the maximum amount that we could make ends up being the smallest number, which in this case is 2. Okay? How do we then interpret some of this extra information? Well, water is now becomes known as the limiting reactant or limiting reagent. Okay? Because it will run out first. What can we refer to our sodium carbonate as? It was present in excess. It can be our reagent in excess. Okay? It doesn't get a fancy name. Okay? So when you're testing your limiting reactant reactions or problems, you have to go through and not do just one conversion, but 2. Or in this case, officially, we needed to do 3. Why 3? There were 3 different reactants. You have to go through and run the calculation at least 3 times. Where does this become extra obnoxious? What happens if instead of giving moles, we gave you grams? You now have to convert it to moles and then convert it across to the moles of the other species. Okay? You have to do a whole bunch of extra calculations. Sorry, I didn't mean to hit you there. Okay? So your limiting reactant calculations will involve a lot more effort and a lot more work. Okay? As far as the exam goes, what you're primarily concerned about is recognizing that mole-mole ratio and being able to manipulate that as far as predicting what was your limiting reagent and so on. Okay? Yes, that is challenging. Questions about that? Okay. Because that wasn't hard enough, we had an extra layer of difficulty on top of that. That layer of difficulty is looking at now a % yield, okay, which is something that you guys did with your copper lab last week. Okay, let's up the ante a little bit. Let's say you were trying to isolate gold. At the end of that experiment, you isolate 0.5 grams of gold versus 500 grams of gold. Which is your best sample to get gold out of? Okay. That 500 gram sample started with a 5-ton sample. Okay. To get 500 grams of gold out, I needed to start with 5 tons. For that half gram of gold, we started with only a half a gram. Which sample is better to mine? The half a gram. Okay. What's the issue there? Well, numbers are misleading. You need to have some way to standardize and normalize your results. That's the goal of a percent yield. Okay? In the case that you guys did with the copper lab, it was relatively straightforward. Okay? We looked at your actual yield. How do you get your actual yield? An experiment. It's what you got. On an exam, how would you get the actual yield? You're going to be told that value. Okay? Theoretical yield. In the lab, that was a little bit different. The theoretical yield, what we're doing is assuming that that sample you started with was pure copper to begin with, or pure gold. Okay? That is the theoretical maximum, because I can't get any higher than that. It doesn't make sense to be any higher than that. Okay? What happens if we now switch it into a chemical reaction instead of a random sample? What is that theoretical yield? To determine the theoretical yield, it is a limiting reactant problem. You would have to go back through and evaluate your reaction. What was your limiting reactant? That's going to determine the maximum amount of product that you could possibly make before you ran out of reactant. That is now your theoretical yield. Okay, so we said limiting reactant was such a pain. You had to carry all this information all the way up and through. Then what do? We move to percent yield, where now not only do you have to carry all of that information all the way up, you now have to do one extra calculation on top of it. Okay? The calculation itself for percent yield is relatively simple and straightforward. It is actual over theoretical. If you're given the theoretical value, all you got to do is take actual over theoretical. Real simple, divide, multiply by 100%. If you have to determine that theoretical value, you now have to go back and test all your limiting reagents, figure out what was your limiting reagent. Okay? Involves a lot of extra calculations that you should be getting very familiar with and very swift with. Okay?
So,
Yes?
or like a question about that would be like, what's your percent yield? And based on the equation that we just used, maybe?
So there are two possible ways that we could ask this, and because we're definitely running a little bit low on time, I won't be able to hit exact examples. If you take a look at the post-lecture calculations or post-lecture problems, I think I gave you two versions of a percent yield question. One version says a student obtained this much and the calculated value was this much. What does calculated value mean?
Theoretical?
It's your theoretical value. So if I tell you the actual and the theoretical value, what do you need to do? Divide them, multiply by 100, you're done with the problem. What if you're not given that theoretical value? You then must calculate it from all of your starting materials. Okay? And that goes back to redoing all that limiting reagent calculation. That is a much more advanced problem. That is not one that would show up on your test. It is one that shows up in the post calculations because it gives you practice for running those calculations. Okay? So the post-lecture calculations do a little bit of both, giving you practice with this material, getting you exposed to the types of questions you can see, and then really making you work to try and get some new challenging questions.
Are you recording this lecture?
Yes, it is. Good question. Okay. What are the units on percent yield? It's kind of a trickier question. There aren't any. There are no units with percent yield, okay? Which makes this kind of a challenging situation. So what units should be used for your actual yield? Because when we get an actual yield, do you have a unit?
Yeah, that's what we're working with.
Yeah, it's whatever you're working with. In the copper lab, it was grams of copper. Your percent yield, though, must be unitless. How do we get rid of that gram unit? The theoretical yield must have the exact same unit. Okay? So if your actual yield is grams of copper, what's your theoretical yield unit going to be? Grams of copper. What if your actual yield unit is moles of copper? Then your theoretical yield unit better be moles of copper. As long as those units match, you're okay to use the equation. If your units do not match, your equation fails, and you will get the wrong answer. Okay, so be aware of that. Okay, we'll see. We might come back, because I think we're running a little bit ahead, but I know these questions can take, well, actually, kind of, sort of. Let's see what we can do here. Maybe someone gave me some numbers. What is the percent yield of mercury sulfide when 0.9 grams is obtained? So it's 0.9 grams of what? Mercury sulfide is obtained from the decomposition of 1.25 grams of mercury 2 thiocyanate. So to calculate percent yields, it's actual over theoretical, right? What's your actual yield? What's the actual number? 0.90 grams of our mercury sulfide. What do we want to divide by? Our theoretical yield, right? How much could we actually make? We're in a lot of 1.25s. I agree. Let's give that a shot. 1.25 grams mercury thiocyanate. Are those units the same? No. If you punch this into the calculator, you get the wrong answer because your units do not match. Okay? To get that theoretical yield, we have to convert that 1.25 grams of mercury thiocyanate into mercury sulfide. Okay? That should sound kind of familiar, like maybe we just did that problem 2 or 3 questions ago. Yeah, we did. Okay? I believe the answer, don't quote me on this, but I think it's right. If you go through and punch in your calculator, get those numbers, you should end up with 1.11 grams of mercury sulfide. I think I did that right. Multiply by 100%, and we now get our percent yield. Okay, remember, to get our 1.11, this is a limiting reactant calculation. We have to go back through and determine or convert our 1.25 grams of mercury thiosulfate into grams of mercury sulfide. That is a pretty long calculation. That's the one we just worked through. Okay, we didn't actually solve it, but I think the numbers come out right. Okay? So this would be an example of one of the longer ones because you'd be expected to run through and do that limiting reagent calculation. Not one you'll see on the final. On the final, I would tell you what is the percent yield of mercury sulfide when 0.9 grams is obtained, okay, when a calculated yield is 1.11 grams. Well, the calculated yield is,
1.11 grams.
which is also your theoretical yield, the exact same thing. Plug it in effectively into the formula and you solve. That's it. Okay? So, could go through a couple other ones. Actually, this one kind of works. If a student were able to obtain 0.35 grams of copper sulfide after reacting, no, this is a long one. Oh God, this is a really long one. We've got 2 reactants that we'd have to check to see if they were limiting reagents. Once we found the limiting reagent, we could then use that as our grams of copper sulfide, or cobalt sulfide. Okay? So this is a really, really long problem. Okay? If you can do this problem, you're probably fine with your conversions. Okay? So it's not a bad goal to work towards in trying to figure this kind of problem out. Okay? The last part that I kind of want to get into, which isn't all that important, but it is part of the curricula, so we need to at least talk about it. There's something known as an empirical formula and a molecular formula. The empirical formula is your fully reduced whole number ratio for an individual compound, okay, for all of the individual atoms. So when we look at, say, sodium chloride, what's our formula? NaCl. But if we're looking at sodium chloride as a solid, there's a ton of sodium ions, ton of chloride ions, all stacked intermittently around each other. Why did we not say sodium 100 and chloride 100? Okay, because we picked the smallest whole number ratio. When we look at magnesium chloride, what do we get for magnesium chloride? MgCl, and we need 2 chlorides. to balance our charge. Why do we use 1 and 2 in that case? We need to balance, and we're using the smallest whole number ratio. What happens if we move to a molecular compound? Okay, so this is where it gets a little bit different and interesting. For ionic compounds, we always take it down to that reduced ratio. Okay, nearly always. Okay, but what happens when we move to a molecular compound? Anybody know the formula for benzene? Just a long shot. C6H6. Okay? If we look at the empirical formula, is this correct? No. Okay? Our empirical formula says that this should be C1H1, the smallest whole number ratio. So when I look at the compound of benzene, why do I not write it as C1H1, but instead write it as C6H6? Because to make benzene, I need 6 carbons and I need 6 hydrogens. Okay? It is the requirement to make that compound, to make that structure. Okay? So why even bother to look at the empirical formula? There are some methods of techniques out there that can allow us to determine the amount of a particular element within a compound. Okay? So what we can do is use that to calculate an empirical rate or an empirical formula. Okay, well, is that really helpful at all? I mean, C1H1 could lead me to benzene, but it could lead me to a half dozen other things as well. Okay? So is that empirical formula helpful? Not really, but it does give me some information. What is that some information?
What's in it?
It has carbon and it has hydrogen. Okay? Which may seem like a ridiculously small amount of information, but consider the size of the periodic table and the possible combinations that we could do with carbon and hydrogen. That is a sizable amount of information behind that. Okay? So it really used to be something super, super important. It has since then lost a lot of that value because we've advanced technology to the point where we can get a lot more information from an individual source without having to do this chemical composition test. Okay? So your empirical formula is just that reduced ratio. And ultimately those numbers give us our moles or atoms within that. Okay? So to go through and do a comparison or do a problem with an empirical formula. If we have this unknown compound and we know it has 0.726 moles of radium and 12.3 grams of oxygen, what is our empirical formula? Well, our empirical formula gives us what? The ratio of moles of each of the elements, and it gives us the smallest whole number ratio. Okay, so what we can go through and do is convert both of our numbers into moles. Totally did that math wrong. Yeah, I did. I think I did. So we could look at our radium. Whoops, come back here. Our radium as being 0.726 moles. And then we could look at our oxygen being 12.3 grams divided by, or if we switch this up a little bit, how do we convert 12.3 grams of oxygen? Okay, and in this case we're looking at oxygen atoms into moles of oxygen atoms. Is there a conversion factor between grams and moles? 16.01? 16. So if we take 12 and divide by 16, we get the moles of oxygen in our compound. We can put that number, whatever it is, there. But when we look at an empirical formula, do we look at fractional numbers? No, we look at whole numbers. How do we get it to whole numbers? That's going to take us up too high and probably still get decimal values. We will go through and divide both of those numbers by the smallest number. Okay, anybody got 12 divided by 16? It's close enough. So what do we do? Divide both numbers by 0.726. What happens when I divide 0.726 by 0.726? I get radium 1. When I get 0.76 divided by 0.726, what do I get? Roughly 1. What's my empirical formula? RAO. There's the empirical formula. Okay? That's how we end up going through and solving. We just relate it back to our moles and slide those into our equation. Okay? How do we convert between our empirical formula and our molecular formula? The relationship between them is a whole number ratio. Okay? There are a couple problems in here to go through and solve. Ideally, you would go through and work with these. There are steps here at the end that break down how you can go through and solve for both your empirical and molecular formulas. Okay? Take advantage of those or use those to try and help you out with your calculations. Okay? We'll go ahead and start the quiz. As I posted online, you can use your notes with the quiz. You can use your exam with the quiz, which is why I passed it back. For those of you that did really well on the exam, can now take a look at it. If you've got extra exam or quiz sheets, go ahead and pass it back. Questions, you can still raise your hand and ask. Doesn't mean I'll answer them, but it depends. Some people have some questions that are not answerable. It is an individual quiz, just so you know. I do have one extra periodic table if you need one.